friends. So I'm currently an MTech student under Guwahati. So what we work on generally are micronanofluidics and fluid instabilities. But what I'm going to present to you today is in silico modeling that I have done 1.5 years back in my BTech. So this was collecting dust, but I felt it should be like relevant to the current conference. So this essentially deals with the computational fluid dynamic analysis of atherosclerosis. So firstly, going into what atherosclerosis deals with, so it's actually like in simple terms, it's the plaque deposition in your arteries. But if we look at the pathophysiology of atherosclerosis, we see that it's a complex series of cascade mechanisms that are involved in a lot of inflammatory processes, which finally determines whether the plaque that is present in your artery is stable or unstable. And depending on certain hemodynamic parameters like say wall shear stress or your upstream blood pressure, so that actually determines whether that plaque is stable or unstable. If this is an unstable plaque, so what it can do is it can get dislodged and it can get stuck in your smaller arteries, arterioles, and capillaries, which can ultimately give rise to ischemic stroke. So this is essentially the structure of the carotid artery. You can see that it's common carotid artery bifurcates into two branches. The internal one is preceded by a bulge. So the motivation that we have gotten at that time was that, so most of the CFD studies or simulation studies, they focused on this stenosis severity. They started with models with no stenosis, then they increased the stenosis gradually, and they wanted to see the fluid dynamic behavior. So that was one part of my thesis that I did. But then I saw that what happens to this plaque geometry? How does this geometry actually determine whether this the disease is severe, or how are the flow patterns altered? So previous literature here, so there are certain studies which were done, say the Tromso study here. It shows that like with greater plaque area, the risk for ischemic stroke is say like proportion, like it's almost a proportional increase, especially for men. So this kind of a knowledge gap is existing that this particular domain is not computationally explored at all. So thereby we aim to actually like create a computational model which actually caters to the hemodynamic parameters like the wall shear stress or the stability of the flow, the pulsatility. So thereby, so we start our simulation in like Omson Multiphysics 5.6 that we use. So essentially when we create the geometry of the artery, we took it from anatomical dimensions so as to maintain a generality in that. So the dimensions are shown here, and while incorporating the effect of this stenosis, we use this very simple formula which takes a fractional cut, and this fractional cut we have used as ellipsoid plaques. So thereby what we did was, since we obtained a 50% stenosed cut, now we varied the plaque geometry. How did we vary was, we changed the major axis. So this major axis length is say done for 5 cases. So it starts from your 3 centimeter plaque deposition length, 3 millimeter plaque deposition length, 5 millimeter, 7 millimeter, 10 millimeter, and 12 millimeter. That's how we varied the major axis, and thereby we got different deposition lengths. Now we wanted to see that for the given length of a plaque, if there is flow happening inside it, is that flow situation actually going to exacerbate your situation or actually make this plaque a stable plaque, which actually reduces your risk for a possible ischemic stroke. So that was the purpose of the in silico study that we endeavored to do. So the hemodynamic parameters primarily were two that we are going to evaluate. So we were taking the instantaneous wall shear stress data. So we took the first order moment wherein we actually did the time averaging of that. And second thing what we did was we took the standard deviation from that mean, and then we normalized it with respect to the mean, and we call this quantity the pulsatility index. This we defined so as to encounter that what is the fluctuation of the wall shear stress from the mean one. Thereby, when we started modeling the blood, so this is one important parameter, that how do we model this blood? So also if you see most of these like computational studies, they simply assume blood to be a Newtonian fluid also, so as to make calculation simple, what we did was we said that let's incorporate non-Newtonian behavior. Now there are several models for that, but the one which is more suited for blood rheology modeling is the Carotid modeling, because we know that blood exhibits Newtonian behavior at very low shear rates and at very high shear rates. In between, it's a pseudoplastic thixotropic behavior that we see. So thereby we use this. The parameters that we have obtained are also from literature, and we actually model the overall properties of blood, like say the density, the thermal conductivity and specific heat by this weighted average fraction, because we know the phi, which is the hematocrit. For the normal value for hematocrit is approximately 0.45, and the rest of the property we took it from plasma. This weighted fraction we used and inputted as the properties for the blood in the material section. Now I'm not going to go into much details for the interest of time, but so actually we impose a pulsatile waveform at the inlet, because the thing is that pulsatile inlet waveform, because arteries generally mirror the pumping of the heart, which is thereby they have a pulsatile flow of blood. So typically, like studies generally assume it to be say a sinusoidal waveform with a damping factor, but that actually is inaccurate. What we tried doing it, we took a kind of a actual flow data set from this study, and then what we did was we divided it by the cross-sectional area to obtain actually the velocity. From flow rate we obtained the velocity, and that we put as the inlet boundary condition here. So this actually gives us a more realistic insight, and we took the systolic time as 0.3 and we extended it to diastolic time from 0.3 to 0.8 seconds. That's the total cardiac cycle time. Okay. Now we use laminar flow physics here, and this is the simulation. We took wall shear stress data, and from there we took the time average of wall shear stress data. This is how it was varying. This is how pulsatility was varying. Now, interestingly, what we saw was for time average wall shear stress, what happens was it starts decreasing as the deposition length increases. This is because the curvature actually reduces, and this flattens out, enhancing Z momentum transfer. But at a certain stage, there is an anomalous increase in both time averaging and pulsatile index. This is due to the fact our hypothesis says that this actually forms a sub-channel inside it. That leads to a turbulent entrance length effect, which thereby, if we increase it too much, then again the flow stabilizes. So this working hypothesis actually elucidates the behavior, and we thereby confirm the same with the clinical studies for populations done. So thereby these trends for 10 and 12 millimeter were explained. So in conclusion, we actually see that beyond the critical length to diameter ratio, the flow actually encounters entrance length effect, and future scope involves actually say making people who are working in microfluidics, they can actually make deformable channels, and thereby we can actually say use PIV and all to validate this kind of a digital film. So with that, these are the references. The details of the study can be found in another paper of mine which deals with the blood pressure analysis. And so thank you. If there are any questions, I can take them up. So one of our studies also won the best paper at ChemCon 2023 that dealt with the blood pressure. This was with the Plaque deposition, which was remaining. Thank you very much. Yes.
Previous slides.
Yeah, sure. This one. Yes.
How wall shear stress is related to plaque stability and fracture?
How wall shear stress? Yeah, great question. So essentially, the plaque structure is the one which is determining whether the plaque will be stable or unstable. Generally, what we see that the more the degree of calcification studies are found, that plaque kind of sits in there, so it doesn't get dispersed. But if it has the degree of calcification is low, this has a greater chance of getting dispersed. So that means if your wall shear stress is very high, that means the frictional force that is acting by the fluid on that plaque is actually very high. So that actually causes an extra force which is basically causing it to disperse. So generally, I have mentioned here the values. So yeah. So typically, if you have say less than 0.4 Pascal, so that is basically say very low wall shear stress. So that actually causes plaque deposition more. But if you have say very high plaque like wall shear stress, that on one hand helps to remove the cholesterol in the bloodstream, as well as what happens is if you have a plaque that has an opposite effect that causes plaque rupture. So that is say very high, so above 0.4 Pascal. So I hope it answers.
How do you get those values?
Yes.
How do you get those values?
0.4 and up. So these are all literature reported values.
Like, is there any proof for
Yes.
like how?
So how do they typically? So these are actually say like these are rather in vitro studies or in silico studies, because in vivo studies are very difficult in doing that. So essentially you cannot actually take out an artery and do that. So what you can do is typically what they do is there is something called carotid Doppler. So carotid Doppler essentially say measures what is say the plaque, that is if there is any plaque that is present. So that carotid Doppler can measure. Also say the velocity at which it is flowing. So from that, so again like here AI comes into picture nowadays as well. So they actually come up with these correlations, and there is something called say physics informed neural networks. So these are called PINMs. So they take into the underlying physics, then they incorporate neural networks, then they use image processing. From all these, they identify these critical thresholds. So I think like for these studies, you can refer a paper by Professor Suman Chakraborty. If you want, I can later give it to you. So they have also like done certain computational studies. They have identified certain critical thresholds, from which we have also taken some of our data.
So thank you very much.
Thank you so much.